shape of the diagram? I mean, how do you know which one is curved, which one is a straight line?
So where the thickness changes, right, is a straight line over here. Okay, whenever you see the thickness changes, it's a step function, right? And
Yeah.
then the rest is just second order polynomial equation, negative higher order. That's it.
Okay, makes sense. Thank you.
Okay. Right. Anyone else? Any question? If you cannot visualize it, then you have to draw. You have to do the functions again, like what I did in the beginning of class. You have to draw this function again. Okay. Okay. If no one has question, let's look at example number 3. Okay. So this is a pretty interesting problem. Okay. So you have a structure. The thickness just change depending on where you are. Okay. From the so on the left hand side, this is the cross sectional view, right? So you can see the thickness at the top is small, at the top is 30, then the thickness changed to 60, then the thickness changed to 90. Then once it passed the centroid, it started reducing again. Okay. And then on the right hand side is the loading of the structure. So if I were to draw the transformation, this is where my X is, Y is, and this is our rotation on Z. On the cross-section view, if I was to sketch our transformation, this is our Y, this is our Z, and then over here is the rotation of our X. Okay, so we have all this information. Okay, so we know still the same formula that we are going to use. Okay, so it asks us determine the largest shearing stress in that section. Okay, so we know that the shear stress is equal to or shear xy is equal to Vy over Izz, okay, Qz over T. Okay, so where T is dependent on the section of interest. Okay, so before we go on, we have to know where is our Vy first. Okay, we have to know what is our Vy first. Okay, so we have to determine Vy. Now, you realize in this course the examples I don't pick easy examples. Okay, I pick examples that sometimes can be really difficult. Okay, so I hope you all learn from the difficult stuff, and then the homework is usually I hope that the homework is easier. Okay, so we know that so I'm going to call this our point A and our point B. Then I'm going to sketch our free body diagram. Right, so our free body diagram, so we know that we have a AY. We are aware that we have a BY. And then given to us, we have a load coming down at 72 kilonewton. And we are given the specific dimensions. This is 0.8. And over here to here is 1.5. Okay. Then we are immediately going to apply, we're going to do static analysis. Where we're going to take summation about moment z at point A is equal to 0. Okay. So the 72 is going in a clockwise direction. So it's negative 72 times 10 to the power 3 multiplied by a distance of 0.8. Then we plus by by, right? And then 1.5 plus 0.8 is 2.3. Whole thing is equal to 0. So we can determine our by is equal to so send 2 power 3 times by 0.8 divided by 2.3. So it's equal to 25.043 times 10 to the power 3 Newton. Okay. And then we have summation of forces in the y direction is equal to 0. So it's AY plus by BY minus by 72 times 10 to the power 3 is equal to 0. So therefore AY is equal to 72 times 10 to the power 3 minus by 25.043 times 10 to the power 3. So it's equal to 46.957. Okay, 46.957 times 10 to the power 3. So from here, what we are going to do is we are going to pick the higher reaction force. Okay, so we know that our V max will be 46.957 times 10 to the power 3 Newton. And why is that? I'm still going to sketch. Don't get me wrong. I'm still going to sketch the shear force diagram for you so you can see better. I don't skip steps. Okay. So if this is my X, okay, and then we have our 0. Okay. I'm going to break this. So 46. So we have 40. So this is our V. Okay. So 46, you'll do this. And then over here, it will go down to 25. And then when it comes over here, By will push it up. So this value is equal to 46.957. And over here is 25.043 times 10 to the power 3 Newton. Okay. So we have determined that our V max or Vy max or Vy is equal to 46.957 times 10 to the power 3 Newton. Okay. So now I'm going to again. So this problem over here, has a very similar problem like what we have before. Is again, we have to identify, okay, we have to identify the maximum, right? The maximum Q over T, or Q over T ratio again. So you can see that the structure is small at the top, the thickness is so small. At the bottom, the first moment, or at the centroid, I'm going to sketch where my centroid is. At the centroid, right? Okay, for one, my bad. So at the centroid, okay, at the centroid, you have the biggest first moment of area, but you also have the widest thickness. Okay. So before we do that, we have to find our I z. Okay. So how I'll find our IZZ is I'm going to section this way. Okay. And this is how I'm going to determine my first moment of area. So this is my section 1, section 2, and this is my section 3. Okay. I did not do the subtraction way because this is just addition. The subtraction way, you have to be really, really careful. Okay. And for this case, when I do it this way, it's just BD cube over 12, BD cube over 12, BD cube over 12. Okay. So the width is 30 for section 1. The depth is 20, 40, 60, 120 cube over 12. Plus, because there's number 2 section, so twice the width is 15 multiplied by a depth of what now is 20, 40, 80 cube over 12, then plus by twice. Then we have the width is 15, the depth is 40 cube over 12. Right, so easy. So this will be equal to 120 power 3 divided by 120 power 3 times by 30 divided by 12 plus 2 times 15 times 80 power 3 divided by 12 plus by 2 times 15 times by 40 power 3 divided by 12 is equal to 5.76 times 10 to the power 6 millimeter to the power 4, or 5.76 times 10 to the power minus 6 meter 4. Okay, let me do it again to confirm. Yep, 5.76. So next we are going to find the first moment of area. Okay. So I'm going to divide this into a few sections. Yeah, I need the diagram so we will not get lost. Can make it bigger. So I'm going to partition this based on thickness again. Okay. So this is looking for point A. This is at point B. And this, I call it C, which represent the centroid. Okay. So remember, the first moment of area cannot cross the centroid, so you only need to look at the top. And we know you don't need to look at the bottom, right? Because first moment of area cannot cross the centroid. So from here, So Q at point A. So let's consider point A first, okay? So Q at point A. So